Hello, everyone, and welcome to Soil Moisture 202, choosing the right water potential sensor. Today's presentation will be 20 minutes, followed by 10 minutes of Q&A with our presenter, Leo Rivera, whom I'll introduce in just a moment. But before we begin, a couple of housekeeping items. First, we definitely want this to be as interactive as we can, so we encourage you to submit any and all questions in the questions pane, and we'll be keeping track of these to answer for the Q&A session at the end. Second, if you want us to go back to repeat something or you missed it or whatever, no problem. We're recording this webinar and we'll be sending around the recording along with the slides via email within the next 3 to 5 business days or so. All right, let's get started. So today we will hear from Leo Rivera, who will discuss how to choose the right field water potential sensor for your application. Leo operates as a research scientist and hydrology product manager here at Meter, and he earned his undergraduate degree in agriculture systems management at Texas A&M University, where he also got his master's degree in soil science. There, he helped develop an infiltration system for measuring hydraulic conductivity used by the NRCS in Texas. Currently, Leo is the force behind application development in Meter's hydrology instrumentation, including the HYPROP and WP4C. He also works in R&D to explore new instrumentation for water and nutrient movement in soil. So without further ado, I'll hand it over to Leo to get us started.
All right. Thank you, Brad, and thank you everybody for attending today's virtual seminar. Today I get to talk about a topic that I really enjoy, which is water potential sensors, and hopefully give you a better understanding of the ins and outs of the different types of water potential sensors. So a little background about myself. I have a background in soil physics and pedology. That's all what most of my research was focused on at Texas A&M and here at Meter. I have over 12 years of experience in measuring and interpreting soil hydraulic properties and soil moisture release curves. In those 12 years, I've gained a lot of experience with a variety of different sensors for measuring water potential in soils, both in the lab and in the field. And it's really helped me have a good understanding of what the advantages and disadvantages are of the different types of sensors, and where they best fit for different types of applications. So I actually want to jump back to this slide. So hopefully some of you guys were able to watch Soil Moisture 102 given by Colin Campbell. If not, I highly recommend going back and watching that video. But in most of our previous virtual seminars, we've talked about soil moisture. And I still see soil moisture as this ambiguous phrase because it's often used to describe two different things about soil. It's used to describe the water content, or how much water is there, or the water potential, which is the energy state, or it's the sum of the matrix forces, the adhesive and cohesive forces, along with some other forces that describe the availability and the pressure that the water is experiencing in soil. So in Colin's virtual seminar, he talked about sensors for measuring water content. And today we're going to talk about the sensors that measure water potential. So before I get too deep into the water potential sensors, I want to try and use an example to help you guys understand the importance of water potential and why I think it's something you should consider measuring. So I want to give an example of controlling the heat or the thermostat in your house. So it may be hard to believe this, but temperature at one point in time was a hard thing to measure, or we just weren't able to measure it at all. And when we had to think about how much heat we needed to give to a room to raise it to a comfortable temperature, we didn't have temperature to guide us. So we had to think about it in terms of heat units, or how many logs we needed to add to a fire to heat that room up. So let's take this room, for example. This is a 90 meter cubed room, and it's currently at 16 degrees Celsius, so it's at an uncomfortable temperature. It's cold. We want to raise it to a more comfortable temperature, let's say around 23 degrees Celsius. That's a temperature rise of 7 degrees Celsius. And again, we don't have temperature to guide our heating, so we just have to start adding heat to get ourselves to a more comfortable temperature. So let's say in this example, this is a dry room. It's no relative humidity, it's just a very dry room. And if you look in this lower right-hand corner here, we have all of these variables right here that we actually have to take into account when trying to figure out how much heat we actually have to add to the room to bring it to that comfortable temperature. One of those important variables is the specific heat of the air, but then of course you have the volume of the room and the density of the air. So these are all important variables that would go into making that calculation. So for a room this size, we would have to add 772 kilojoules of heat to raise the room temperature 7 degrees Celsius. Okay, so let's just say we now have the same room, but it's at 50% relative humidity. And we still want to try and achieve that same 7-degree rise in temperature to take it from 16 degrees to 23 degrees Celsius, a more comfortable temperature. In the case of 50% relative humidity, we see a change in these variables, specifically the specific heat of air. And that one change in variable results in us now having to add 1,472 kilojoules of heat. So almost double the amount of heat needed to raise the room that same temperature. And I want you to think about this in terms of soil and adding water to soil. It's the same concept. We can't just use water content alone to understand how much water we need to add to make the plants happy, for example, to bring that to a more a water potential where the water is more accessible for the plants. And we would have to know about the properties of soil to make that decision or know when we're at a good point. Whereas if we had matrix potential, we would know exactly what the water status is in the soil, and it's very easy to control to that point. But the thing about measuring matrix potential is it's very difficult, and there's not one sensor that fits all. So let's look back at the history of measuring matrix potential in soils. Let's go back as early as 1900. It actually started with something called the Livingston cone, which was just a ceramic cone that you would put in the soil. We knew about the properties of the ceramic cone, and then we could use that, pull it back out later and measure it and see how much water it gained to figure out what the matrix potential was in the soil at that point. This is obviously a very manual step. As time went on, we started coming out with sensors that actually were electronic. For example, electrical resistance sensors, which gave us the ability to actually make a more digital measurement of, and a more continuous measurement of matrix potential, but these sensors were flawed. We continue to evolve and make new technologies like tensiometers and heat dissipation sensors, and then eventually capacitance-based sensors. But with all of these sensors, as time has gone on, they've had one main issue. They don't cover the full range of water potential. And as we've continued to evolve and develop technology, we've really had one goal, and that's trying to build a sensor that can measure the full range of water potential accurately. I have a link below to a blog in environmentalbiophysics.org that talks about the history and future of water potential sensors. I highly recommend taking a look at this blog if you want to learn more about this. So ultimately, the challenge with measuring water potential in the field and in the laboratory is that there is not one sensor that measures the full range. So here we have a chart that shows the ranges that different types of sensors and laboratory instruments work well at measuring water potential. And as you see, there's not one sensor that covers the full range of water potential. And some cover a larger range, but they have less accuracy. Some have very good accuracy, but they don't cover a very large range. And this has been the challenge when trying to measure water potential in the field. And it's why people tend to rely on water content, because it's easier to measure. But there's a lot of value in measuring water potential, and we're continuing to try and strive to improve that measurement. And ultimately, our goal is to build a sensor that can measure this full range, and that's what we continue to push for. So let's talk a little bit about the different field sensors that are available for measuring water potential in situ. So we start with solid equilibration methods, where we have a matrix. We have a matrix that we put in soil and that equilibrates with the soil, and we use that to measure the water potential. So we have electrical resistance-based sensors, we have capacitance-based sensors, and we have thermal conductivity-based sensors. All of these are based on the same principle of that solid state matrix. And then we have liquid equilibration methods, like tensiometers, where we're actually measuring a physical force that the soil is applying. And then we have vapor equilibration methods, like a thermocouple psychrometer, where we're actually measuring the relative humidity of the soil and then using the Kelvin equation to determine what the water potential is. All of these different sensors have different advantages and disadvantages. In this talk, we're primarily going to focus on capacitance-based sensors and tensiometers. So let's start with solid matrix sensors. A solid matrix sensor starts with having a consistent matrix with known characteristics. You can have a matrix made of ceramic, you can have a matrix made of different size granules, but what you ultimately need is you need a consistent matrix if you want to be able to build a sensor that can make consistently make good water potential measurements with a variety of different sensors. So you can have multiple sensors that all can measure accurately. So typically we want to have this consistent matrix that we know the properties of. So we want to know the retention curve or the retention characteristics of that material. And what we're doing is we're measuring as the material begins to desaturate, as it's in equilibrium with the soil, we're measuring the change in the water content of that material and using that to output an apparent soil water potential. So one of the common techniques that's used with a solid matrix sensor is a capacitance-based solid matrix sensor. So with a capacitance-based solid matrix sensor, we're using a ceramic solid matrix, and we install that ceramic solid matrix in the soil. And what happens is, as it's installed in the soil, it's going to come in equilibrium with the water potential of the soil. And that's the beauty of water potential, is it always wants to be in equilibrium. So when you put something in contact with the soil, it's going to come into equilibrium with whatever that energy state or the water potential is of the soil. So if the soil is wetter than the ceramic's going to pull in water from the soil until it comes into equilibrium with the water potential of the soil. As the soil dries, if the ceramic's wetter, then the soil will begin to pull water out of the ceramic until, again, it comes into equilibrium. It's always trying to be in that equilibrium state. And what we do is we actually measure using capacitance-based technology. We measure the water content of the ceramic. So we have a confined electromagnetic field within the ceramic that is measuring the change in water content of the ceramic. And we know we built the ceramic to have a very consistent matrix, and we use a capacitance-based technology to measure what the water content is. And then to get as good of accuracy as possible, these sensors are actually calibrated to output a water potential based on the ceramic characteristics. So what I'm saying by they're calibrated, we try to build ceramics as consistently as possible, but it is nearly impossible to make a perfectly consistent ceramic time after time. And so because of this, we actually have to do individual calibrations for each sensor. And that is crucial in making a more accurate measurement with this sensor type. So with solid matrix sensors, there are advantages and disadvantages. One of the main advantages of a solid matrix sensor is there's no maintenance needed for a solid matrix sensor. And most solid matrix sensors have a relatively large sensing range. So typically they can measure between -10 and -2500 kilopascals. So that covers the plant available range typically. And if they're calibrated, you can have really good accuracy for a solid matrix sensor that doesn't require any maintenance. The disadvantages to solid matrix sensors is that the calibration or the accuracy is dependent on calibration. So if you're using a non-calibrated solid matrix sensor, you're not going to get as good of a measurement of water potential. Another disadvantage of solid matrix sensors is they do have limited wet-end performance. So due to the air entry of the ceramics and the different materials, typically we're not able to measure with these types of sensors between 0 and -10 kilopascals. Now this is something that a lot of us are working on. We're trying to extend those ranges and trying to push it further into the wet end, but up to this point, we're still limited in this range, and hopefully in the near future we'll be able to change that. One other disadvantage to solid matrix sensors, and it's a little bit dependent on technology type, but as you can imagine, as you start to approach lower water potentials, there is less water in the ceramic, and typically it's a very small amount of water in the ceramic. Because of this, the solid matrix sensors typically tend to be have a little more temperature sensitivity because of the small amount of water that's held within the ceramic. So that's just something you need to be aware of as you're thinking about these about solid matrix sensors. So now let's talk about liquid equilibration techniques. So Well, the liquid equilibration technique, typically what we start with is we have a ceramic or a porous matrix. Typically it's a ceramic cup filled with water. That ceramic cup is filled with water in the soil. And again, because we're dealing with the energy state, the soil begins to pull on the water in that ceramic cup. And we're actually able to measure that pull that the soil is applying on the water in the ceramic cup. Typically, this is done with some type of pressure sensor, whether it's a manual dial gauge or a digital pressure sensor. As the water potential begins to decrease, obviously that pull is going to get higher. And so we're just measuring that increase in suction that's being applied as the water potential decreases and the soil is trying to pull on the water in the ceramic cup. Now, with most liquid equilibration techniques, one of the main issues is eventually you get a high enough vacuum or high enough suction that the water actually reaches a boiling point in the soil. So typically when you get below about minus 90 kilopascals, the sensor cavitates and an air bubble forms. And once that air bubble forms, then tensiometers are typically not able to measure anymore. So that's why they have a limited range in the wet end. Now, some of the other issues that we've had with liquid equilibration based sensors is typically they've had large water columns. And so with that, they have corrections that you would have to make based on the depth that you have the sensor and how tall that water column is. And so that made them a little more difficult to use too if you're trying to get an accurate water potential measurement. So as tensiometers have continued to advance, I mean, they've been around since the 1960s. What we've really been pushing on with tensiometers is trying to improve the measurement technology. So we've moved to digital pressure transducers. We've also tried to improve things like reducing that water column. So most tensiometers nowadays have a very small water column that's only held in the ceramic, and the digital pressure sensor is going to be right at that interface with the ceramic, and that reduces the correction that you have to do for that water potential measurement. So trying to remove the water column, and then of course the other issue with tensiometers is the fact that they cavitate. So this means that you have to come out and refill them. So what we've been trying the goal with tensiometers has been to try to improve that experience and make it easier to refill these. So many tensiometers have external refilling tubes that make the process of using tensiometers a lot easier. One of the main advantages of tensiometers is their accuracy. There's nothing that's going to come even close to the accuracy of a tensiometer in the wet range. And because of the way they're measuring, not only are they able to measure the suction that's being applied, but they're also able to measure positive pore pressures. And that can be really advantageous when we're trying to look at things like slope stability. And when we're also looking at groundwater exchange and groundwater movement. So tensiometers are a really powerful tool when we're looking at water movement in soils and really looking at the wet state of soils. But although we've made a lot of advancements with tensiometers, they still have a limited range. This is not something that we've really been able to overcome. There are some types of sensors that have used different liquids and different polymers to try and improve this, and they have improved the range, but that tends to sacrifice the accuracy of the sensor. So what are the advantages and disadvantages of tensiometers or liquid equilibration techniques? One of the main advantages, again, is they have the highest accuracy of any sensor in the wet range. And because of the way they measure, they're also able to measure positive pore pressure, which can be a really valuable tool. Tensiometers are one of the most commonly used tools nowadays in slope stability monitoring because slopes tend to fail when pore pressures go positive or when soils become saturated. So they're really useful when trying to look at that. The disadvantages to a tensiometer, again, are the limited range. So in terms of water potential, they can only measure down to minus 90 kilopascals. And because of cavitation, they do have a significant maintenance requirements when needing to come out and refill the sensors. So given all of that, and when you're trying to think about what sensor you need to use for your research, there are some things that you need to think about. And ultimately, it almost always comes back to the ranges and the range that the sensor is going to work in. So the first thing you need to think about is, what is your application? Are you trying to measure water fluxes in soil? Are we trying to look at plant stress? So obviously, if we're trying to measure water fluxes, the tensiometer is going to be a much better tool. Or if we're looking at plant stress, we're going to want a sensor that's going to cover a larger range, and especially that's going to cover the plant available range. So a solid matrix sensor is going to be quite a bit more powerful for that. But you also have to consider, what is your soil type or media, and what are the expected water potential ranges. So in soilless media and in sandy soils, typically you're going to be in that wetter range if between wetter than -100 kilopascals. So in this case, you actually might be better served with a tensiometer. Even if you're looking at plant water interactions with this material, you're still better served because you're going to have to stay in that wet range with soilless media and with sand. Whereas with finer textured soils, you're often going to be well beyond the range of a tensiometer. And so you have to think about that as well. And then again, what are your maintenance needs, or what are the maintenance requirements of the sensor? And is the site accessible? How often can you go out if you do need to refill a tensiometer? Is it even possible? If not, then you might want to consider a solid matrix sensor, even if it sacrifices a little bit of accuracy. It might still be the better choice, just in terms of actually managing and having a good data set. So I put together this little table here just to kind of help you think through the different sensors. With many of the solid matrix sensors, they don't come calibrated from the factory. So you want to make sure if you have the ability to do a calibration, then you could use some of these different sensors and do a calibration in-house. It does take a lot of work. It's something we spent years on trying to develop a good system for. What are the maintenance requirements of the different types of sensors? And what is the accuracy? So with the thermal, for example, thermal conductivity based sensors, their accuracy is going to be dependent on calibration. And then with tensiometers, you have the best possible accuracy, but you're going to have those maintenance requirements. So you have to think about refilling and also frost protection. These sensors are susceptible to freezing if it's going to freeze down to that depth. So you have to make sure that you understand that, and if needed, you will have to come out and remove the water from the sensor, or just pull the sensor out entirely if it's going to freeze down to the point that the sensor's at. So what are the keys to using water potential? So we've talked about water potential sensors and the different types, but what are the keys to using water potential to actually get good data? Even if you choose the right sensor, there are other components that go into that to getting good water potential data. So when you're thinking about this, you really have to look at it from a system view. And ultimately, it starts with installation. If you want to get good water potential measurements, and the same with water content measurements, it ultimately starts with having a good installation. What are the keys to getting good measurements? Well, with water potential sensors, good soil contact is critical. If you do not have good contact with the soil, then it's going to take longer for the sensor to come into equilibrium with the water potential of the soil, because it's going to have to do it in vapor phase in many states. So it's really critical that you have good contact. So for example, with solid matrix sensors, it's often a good idea to pack soil around the sensor before installing. And you want to make sure you have a nice tight hole for the sensor to go into that will have the least chance of soil shrinking away from the sensor later in the season. And the same with tensiometers. You may want to make sure you auger a hole to the size of the tensiometer that will allow it to have good contact with the soil. Another piece with tensiometers is actually understanding how to install the tensiometer. If you're using a tensiometer that has a large water column, you have to take into account your water column height. This also means you're going to have to take into account your angle. And also with tensiometers, typically you have the refilling tubes that need to come to the surface. So they'll typically have shafts that allow it to run to the surface. So you'll select your shaft length based on the installation depth that you want to go to. And then you'll try and run those pieces to the surface. I often recommend having the shafts slightly below ground and protected in something like an irrigation valve box. That way the refilling tubes are still accessible, but the sensor itself is protected from any potential damage from tractors or the sun beating down on the sensor. A lot of this really ultimately comes down to having the right tools. So for example, tensiometers, we have augers that are sized specifically to the tensiometer and then taper down at the end. And this really helps ensure that the sensor itself has good contact. And when you're choosing solid matrix sensors or trying to go out and install solid matrix sensors, you want to choose tools that are going to help you install them more easily without having to make large holes. And really, a lot of this ultimately comes down to protecting your installation. One of the most common issues that we see with installations and with getting good data and people not being able to get good data is the installations aren't protected. And one of the main things is protecting the cables. You need to make sure you protect the cables from any rodent damage. They need to be protected from tractors and various things. So when you do an installation, it's really critical that you also protect the cables to help ensure that that you continue to get data throughout the season and you don't have gaps in your data. And another piece to really having a good installation is actually trying to minimize site impact. If you have to dig a large trench to install your sensors, that sometimes is going to impact the quality of your data for potentially a long period of time, maybe even up to a year. There's different thoughts on this in different areas, but if you can minimize site impact, that's going to help you ultimately have better data down the road. The nice thing about tensiometers is you can auger a small hole to install them, and it does make them quite a bit easier to install, and also it reduces site impact. So another piece to getting good water potential data or utilizing water potential data is how can we use it to best understand our soil? And one thing that often is really helpful is actually knowing the retention characteristics of your soil. So here we have retention curves. These are laboratory derived retention curves of 3 different soil types. And we see they all have different retention properties. And if we can do things like use a combination of water content and water potential sensors in the field, this would allow us to develop the same understanding of the soil based on field measurements. And here we have an example of a portion of a in situ retention curve that was collected using in situ soil moisture sensors. So this was collected using a Teros 12 soil moisture sensor, and then the Teros 21 capacitance-based solid matrix sensor. And we were able to collect a really nice piece of the in situ retention curve using these 2 sensors together. And what you can see is it actually fits along pretty nicely with the shape of a curve from a silt loam soil, which is what we would have expected, knowing that we're primarily working in silt loam soils in this field. The value in this is it gives you more information and helps you better understand how you would need to do things like irrigate. Again, these can be used in situ for slope stability using these two pieces together. So really just it helps you have more information and more a better understanding of your soil. And another key piece in getting utilizing and having good water potential data is having access to your data and being able to visualize your data. So using things like cellular enabled data loggers so you can transmit your data remotely, being able to go on and actually view your data and see where your loggers are at, and actually being able to look at your water potential data or water content data in near real time. And so this is a key piece. Another part of actually being able to utilize your water potential data is now we have the water potential data, can we use it to make decisions? And ultimately that's our goal, is to be able to take our real-time water potential data and make decisions about things like irrigation or the potential for slope failure or various other things that we may want to try and look at and understand about our soil. So in conclusion, the keys to choosing the right water potential sensor really ultimately lie in water potential ranges and accuracy, and what are the maintenance requirements for that sensor and how can they best be used for you. And keys to using water potential really installation is key. And then being able to look at your data and visualize your data and use that for decision making.
Awesome. Great. Thank you, Leo. We do have a couple minutes. We'll squeeze a couple minutes in here to take some questions from the audience. We've got several. And if you do have a question, now's the time. You can add some more questions to that questions pane. If we do not get to your question, we do have them recorded, and Leo or someone else from our team will be able to answer you via the email that you registered with. So again, ask any and all questions that you have, and we'll try to get to as many as we can here in the next couple minutes. So first one here, let's see. Can the relationship between soil moisture and water potential in the range of accuracy of the water potential sensor be used to infer water potential from soil moisture readings in drier conditions?
Yeah, that's a really good question. And that's actually a pretty common approach that's taken by a lot of people. You can use either you can try and develop that relationship in situ and then try and infer a little bit further down what the drier condition water potentials are. And you can use things like different Van Geneuchten functions. There are functions available that you can use to try and fit those data, and then actually take water content data and try and infer what your water potential is in those drier states. So yeah, that is an approach, and it's actually pretty commonly used.
Okay, and kind of along those lines, what sensor might be appropriate in more arid environments when the solid water potential might be very low for a lot of the year?
That is a really good question, and it's the one sad thing is that probably one of the better sensors for measuring in really dry conditions is one we didn't talk a whole lot about, but it's the vapor equilibration. So a thermocouple psychrometer is really useful in really dry conditions because we can use that relative humidity measurement. The problem is they're really hard to find. I just had this conversation. They're not as readily available commercially anymore, but that might be a really useful tool there.
Okay. Let's see here. Can you use water as a control, Leo?
Well, I think ultimately you need to know what you're trying to control too. And this is when you think back about water content, you can't just control to water content unless you know a lot about your soil. And so this is why water potential is such an important factor. If you know a lot about your soil, you can make better decisions based on water content, but really a lot of it comes down to knowing knowing what the energy state is going to be.
For tensiometers, if you're looking to measure potential at a specific root depth, how do you know what depth to install the sensor with a long water column?
Yeah, so that's a really good question. So with tensiometers, if you're using a more traditional tensiometer that has the long water column in it, you're gonna, as long as you install the ceramic cup itself at the depth that you're trying to measure at, then you make corrections based on the height of your water column. So for example, if your water column is 10 centimeters high, then it's 1 hectopascal per, is that right? I think that's right. 1 hectopascal per 10 centimeters. So essentially there's a correction based on your height, and you would just offset your data based on that value.
How about case studies? Are there case studies for plants and turf available?
So that's a really good question, and hopefully I'm understanding what you're referring to here. But there are a lot of case studies about different types of plants, specifically what water potential ranges they're happy at. Actually, there was a paper done by Sterling Taylor that gathered all of this information about different plants and what water potential ranges are appropriate and where they're happy and how long they can go before they're not happy. But there's also a lot of work being done looking at, I know there's folks down at BYU and various other locations that have been doing work using both in situ water content and water potential sensors in turf. So there is work being done in that area.
I think we'll have time for about one more question. Again, if we do not get to your question, we have them recorded. We will get back to you via email. Okay, last one here. One of the most important equipment that is missing in irrigated agriculture is a reliable, reasonable priced tensiometer with pressure transducer. Is Meter Group working towards providing that to growers and researchers?
Yeah, so that's a really good question, and actually I think that's a really good point. Traditionally, tensiometers, a good tensiometer with an accurate pressure transducer has cost typically around $900 per sensor. And this is actually something we've been working pretty hard towards. And so we actually just released the Teros 32, which is a lower cost tensiometer. It's more towards the cost of our solid matrix sensor, the Teros 21. So we think it's a step in the right direction for that application, because we do see that we need a lower cost tensiometer that still has the same accuracy. So it is something we've been working on. I think the Teros 32 is getting us more in that area. It may not be exactly where we need it to be, but it is something that we're moving towards. So I hope we're able to help fill that void.
Awesome. Thank you, Leo. And again, thank you to all of you who have been listening in. We have tons of questions that have come in and have not had time to address them all. Again, we will get back to you. And if you have any other questions or want to know more about water potential sensors, please visit us at metergroup.com, and we'll be able to help you out and help you figure out what sensors are best for your applications. We hope you enjoyed this discussion as much as we did. Again, thank you for all the great questions. And please consider answering the short survey that will appear after the webinar is finished to tell us what other kinds of webinars or topics you'd like to see in the future. Also, look for the recording of today's presentation along with slides in your email inbox. And again, stay tuned for future Meter webinars. Thanks again, and have a great day.